Okay, everyone, assalamu alaikum. I hope you guys are all well. So let's begin. So we are going to cover 3 different topics today. In fact, we're done with one already in the last session, in which we covered the concepts. For that topic, we will be doing practice questions today. That's circle properties. And then we will be covering functions and the concept of HCF and LCM today. That's the plan for today. And then in the next class on Wednesday, inshallah, we start mensuration. Okay, now let me quickly remind you about what we did in the last session. We talked about these angle properties of in a circle. So we started with some basic definitions, that's some terminologies that you need to understand. Segment, what a segment is, and then these terminologies: tangent, radius, diameter, chord. You need to know about these. And then there were some properties that we covered, like radius is perpendicular to tangent. We talked about this property. And then if you have a line coming from the center of the circle to a chord such that it makes a 90 degrees, the chord is divided into 2 equal parts according to this property, and it works both ways. If you know that this point is the midpoint, then the angle is going to be 90. And if you know that the angle is 90, then the point is going to be the midpoint. So if you know one of those 2 things, the other is implied from that. Then we talked about this next property where we said angles in the same segment are equal. So if we have a chord like this, and that's making angles in the circumference at different points, for example, these were 3 angles that this particular chord was making, all of those angles are going to be equal to each other. We looked at this property. Then we talked about this one where angle at center is twice the angle at circumference. So if you have a chord that's making an angle at the center of a circle, for example, if you have this chord AB, it's making an angle at the center of the circle, and it's making some angle at the circumference of the circle as well. The angle at the center is going to be twice the angle at the circumference. We did a couple of examples in this. And we talked about angle made by a diameter. So angle makes 90 degrees at the diameter. And then cyclic quadrilateral, if you have a quadrilateral that has all its vertices, all its corners at the circumference of a circle, the opposite angles in that cyclic quadrilateral, they always add up to 180. Okay, we call these supplementary angles. If the angles add up to 180, that's another property that we did. And then if you have 2 tangents coming from a point outside a circle, those 2 tangents are always going to be equal. And whenever we have a shape like this, whenever we have 2 tangents like this, what we always do is we make a kite-like figure that helps us with calculations, because in this kite figure, if you break it down into 2 parts from the middle like this, by drawing this line, we get 2 right-angled triangles, and they're congruent triangles. They bisect the angle. This angle is equal to this angle. This angle is equal to this angle. This is what we talked about in the last session. And then finally, we talked about this alternate segment theorem, in which if we have a cyclic triangle, this has been added to the syllabus recently. It was not part of your syllabus earlier, but now you need to know about this as well. Cyclic triangle, that means you have a triangle in a circle that has all its vertices on the circumference. And then at one of those vertices, for example, we have 3 vertices here, A, B, and C. If we have a tangent at any one of those vertices, for example, if we have a tangent at A, and this tangent makes some angle with one side of the triangle, for example, this angle X, then this is going to be the same as the angle, as the interior angle on the other side of the triangle. So the angle that's opposite to this side inside that triangle, that's going to be equal to the angle X here. Similarly, if we consider the angle Y outside this one, that's the angle with the side AC of the triangle of this tangent. This is going to be equal to the opposite interior angle in the triangle. Okay, This is called the alternate segment theorem. We talked about this. And then finally, this is one thing that used a lot in circle questions. It's not a property as such, but something that you need to also keep in mind, that if we have a triangle that looks like this, where two sides of the triangle are the radii, like this, then it's always going to be an isosceles triangle. We have two sides equal. What that means is the angles opposite to those sides, angles opposite to the radii, they are going to be equal to each other as well. Okay, so this is what we did in the last session. We covered all of these properties. Now today we're going to start with some practice questions on this before we cover two more topics today, two short topics, functions and HCF and LCM. Okay, but let's start with some practice questions on this first of all. Okay, so these worksheets are uploaded on Classroom. I hope you've started attempting questions from them. Let's have a look at some questions from this. First of all, what if there's no center? Yes, in that case, we don't use these properties. So if the center of the circle is not given, when did you send this message? Okay, the very end. So I suppose that's related to this last property. If that's the case, then if this is not the center, that means these are not going to be radii. In that case, we can't assume. In this case, we cannot assume that these angles are equal. This is only in case where these sides are radii. Okay. So all the properties that involve the center of the circle, for example, angle at center is twice the angle at circumference. This only applies when you have the center, of course. And this property here. So the properties that involve the center, they only apply when you do have the center given in the question. But let's have a look at some examples to understand how they're going to be used. Now, these are questions from the worksheet. Let's start with some relatively simpler ones. Okay, we'll see some of them, Afifa. We'll see some of them here in this worksheet. Okay, so we say, let's say we have something like this. A, B, and S are points in a circle, center O. TA and TB are tangents. ATB angle is 52 degrees. We need to first of all find the angle AOB. Okay, now how do we think about this? Let's write down all the angles that we can clearly see in this diagram, and then we'll start talking about the angles that we have to find out. Okay, so we have a situation like this. We're given two tangents, TA and TB. These two tangents are equal to each other because these are tangents coming from the same point outside the circle. This figure, remember, is going to be a kite. So if I join these like this, O is the center of the circle. This is a kite where this angle is 90 degrees. This angle is also 90 degrees. If this angle is 52, and the sum of all angles in a quadrilateral is 360, what about this angle? We can also figure this out, right? This is going to be 180 minus 52 because the sum of all four of these angles, this is 360. If this is 90 and this is 90, then these have to add up to 180 as well. So we can find this angle. That's going to be 180 minus 52, which gives you 128 degrees. So this angle here is 128 degrees. Okay, now let's see what they're asking us to find. Okay, so that's the first angle that they actually want us to find, AOB. What's that going to be? That's going to be 180 minus 52 degrees. That's 128 degrees. Because of that kite-like figure that we have, all the angles add up to 360. So that means this angle has to be 128 degrees there. What about OBA now? OBA. What exact angle is this? OBA. Let me mark that here. OBA angle is this little angle here. Now we have already figured out that the angle at this point is 128 degrees. All right. Now, how do you find this angle? Now, the last thing that we just discussed, we have the center of the circle here, and these two lines are the radii of this triangle. If you're looking at this triangle, it's an isosceles triangle. Why? Because two sides are equal. This is radius, this is radius. That means the remaining two angles, which are this angle and this angle, they are going to be equal to each other because of this being an isosceles triangle. How do you find those remaining angles? Sum of angles in a triangle is 180. So what we can do is we can subtract from 180 this 128 degrees angle, and that gives us the sum of the remaining two angles, right? 180 minus 128. This is going to give you 52 degrees. That's the sum of this angle here and this angle here. Now, since both of those angles are equal to each other, we can divide this by 2 to get one of those angles, and that's 26 degrees. So the angle OBA, therefore, that has to be 26 degrees. No, it's not an equilateral triangle. It's an isosceles triangle because we have two sides equal. This is R, this is R. The third side is clearly not equal because this angle is 128 in an equilateral triangle. All angles are supposed to be 60 degrees. This is clearly not that. This is isosceles. Okay. ASB. What about ASB now? ASB is this angle here. How do you figure this out? Which property can we use now? Let's think about it. We have this chord AB. This chord AB is making one angle at the center. What's that? That's 128. Angle at the center is 128. What about that same chord making another angle at the circumference? So we have a chord that's making an angle at center, that's 128 degrees. And that same chord is making an angle at the circumference. Angle at center is supposed to be twice the angle of the circumference. So that means the angle of the circumference is going to be 128 divided by 2, and that's 64 degrees. Okay, the angle at circumference is half the angle as compared to the angle of the center. Angle at center is twice. Okay, so in order to get from the angle at the center to the angle at the circumference, we have to divide that by 2, and that gives us 64 degrees. That's the angle ASB. All right. Okay, now let's have a look at another example. Let me just adjust the pen size quickly. Okay. Let's try this one. In the diagram, the points A, B, C, and D lie on a circle, center O. A or D is the diameter, OB is parallel to DC, and BOD is 140 degrees. BOD is 140 degrees. Okay. We need to find the angles X, Y, Z, and T on this diagram. Okay, now how do we think about this? First of all, they want us to find the angle X. Okay, now for this, we can use that same property, isosceles triangle. Why? Because we have this triangle OBD, right? This is an isosceles triangle. Two sides are radii. So the base angles of this isosceles triangle, they have to be the same. If this is X, this is also supposed to be X. How can you find any one of those angles? We can directly do 140 minus 180 minus 140 divided by 2, and that will give us 20 degrees. Or another way to think about that same thing could be that we could say X plus X, that's the angle, and these are the same angles in the isosceles triangle, plus that third angle, which is 140. They should add up to 180, and that gives us the same thing as above. That's 2x plus 140, which means 2x equals 180 minus 140, and x equals 180 minus 140 divided by 2. The value of x turns out to be 20 degrees. All right. So x equals 20 degrees. That was one angle that we were looking for. What about y now? What about y? This angle here. How can we think about this angle y now? Any idea about this angle y? Okay, now there could be multiple ways of thinking about this. One thing that I'm thinking of is that we can say we have this chord BD. Let me highlight that. So we have this chord BD. This chord is making an angle at the center. Now, the angle at the center is 140. This is the angle at the center. Now, if this chord were to make an angle at the circumference, what would that angle be? That would be half of that. The same chord is making this angle at the circumference, the chord BD, that's making 140 at the center. And that same chord BD is making an angle of BAD on the circumference. What should that angle be? That should be half of 140. So this angle should be 70 degrees. Let me write that down here. For the second part, I can say the angle BAD, that should equal 70 degrees. Why? Because angle at center is twice the angle of the circumference. Angle at center is 140. We divide that by 2, and that gives us 70 degrees. That's the angle at the circumference. And now, how is that useful for finding y? Now, if we look at this bigger figure, 1, 2, 3, 4. It's a quadrilateral. It's a cyclic quadrilateral with all its vertices on the circumference, right? So we have a cyclic quadrilateral now. This angle 70 is opposite to the angle y. What that means is they should add up to 180. So y plus 70, that should equal 180, and that gives us y equal to 110. That's the value of y that we get. Okay, let's look at C now. Z. Okay, how can we find the angle Z now? Let's think about that. Angle Z. That's the angle made by the chord BC. So now let me just get rid of this. Highlight here. Okay, so what do we know until now? Let's mark those angles. We know that this angle X is 20 degrees. We know that this is also 20. This angle here, that's also 20. What else do we know? We know that the angle Y is 110. We know this angle as well now. All right, so these are the angles that are known to us now. Okay, let's think of how we can find the angle Z after this. So if we consider the chord BC, that is giving us only one angle at the circumference that we've already found. Okay, so we can actually use those parallel lines here. We have those two parallel lines. We have one line OB and we have another line CD. These lines are parallel lines, right? And there's a line that is passing through those parallel lines. That's this line BD. This line BD is passing through, is intersecting those parallel lines. This angle 20 and this angle Z, these are alternate angles, right? This angle 20 here and this angle Z, these are alternate angles. So that means the angle Z should also be 20 degrees. Z is also going to be 20 degrees. Why? Because these are alternate angles. If this angle is 20 here, Z here should also be the same. This one and this one, these are alternate angles. All right. Then we have to find the angle T. That's straightforward now. Once we have the angle Z, we can think of this triangle now, BCD triangle. In this triangle, we already know two angles. One is 110 and the other we found to be 20 degrees. What's the remaining angle T? That would just be 180 minus 110 minus 20, and that turns out to be 50 degrees. So this angle is supposed to be 50 degrees. All right, this is what we have. There could be another way of thinking about this as well, but that gives us the same thing. That's okay. So this is the value of T. That's what we were looking for. Okay, I hope that makes sense. Now let's have a look at one in which you're saying a circle is not involved. Now make sure that you write down those answers in the space that's provided here. So this is 20, this is 110, and then you have 20 again, and then you have 50 at the end. Okay. All right, now let's have a look at one in which they might not have given the center, or that might not be used. Okay, let's try this now. This is question number 13 from the spreadsheet. Let's try this. In the diagram, the points A, B, and C, A, B, C, and D, they lie on the circle. BD is the diameter. Okay, BD is the diameter. Okay, this is the diameter. The tangents from T touch the circle at B and C. The tangents from T touch the circle at B and C. Okay. ACB is 52 degrees. You've got those two angles given. Okay. Now, if BD is a diameter, let's mark some angles quickly, which are easy to figure out. This angle is supposed to be 90 degrees because this is the angle made by the diameter. And similarly, this whole angle, this complete angle should also be 90 degrees because again, it's the angle made on the circumference by the diameter. Okay. So these two angles, they have to be 90 degrees. Okay. Now, since these two tangents are supposed to be equal to each other, tangents coming from a single point outside the circle, this triangle that we see here, this is an isosceles triangle. That means this angle opposite to this side, if that is 56, the angle opposite to this side should also be 56. So this angle should also be 56. Okay, now let's look at what they're asking about. They want us to find the angle BTC first of all. Angle BTC. BTC. Okay, so that's the angle that we're looking for, this angle here. Now, how can you find this angle? We've already figured out that this angle here has to be 56. If that's 56, now we've got this triangle. The sum of all angles in a triangle is supposed to be 180 degrees. We can find angle BTC like this, 180 minus 56 minus 56, and that will give the result. That should be 68 degrees. Yeah, 68 degrees, and that's the final result that you get from this. Now they're asking us for the angle ADB. ADB, that is this angle here. Okay, now how do we think about this? Where is this angle coming from? It's made by the chord AB. AB is making one angle at the circumference here. Is it making any other angle at the circumference that you might know something about? It's also making this angle at the circumference. This is 52 degrees. If that's 52, then this angle here should also be 52. Okay, angles in the same segment, angles made by the endpoints of the same chord in the same segment are supposed to be equal. So the angle ADB therefore is also going to be 52 degrees. Okay, using angles in the same segment property, this angle here is also 52 degrees. All right, let's move on. BDC. BDC. Okay, what's that angle now? BDC. That is this angle here. Okay, now how do we think about this? BDC. Okay, so what do we know already? We know that this is a right angle. Okay, and this whole thing is also a right angle. Now keep that in mind while we try to figure that out. What about the remaining angle now? How do you figure that out? Okay. Now, what about this remaining angle? If the whole angle was 90 degrees, if this is 52, what's this remaining angle? This is going to be 90 minus 52, which is 38 degrees. So we have this angle here. This is 38. Okay. Now, what else? Is this a kite-like figure? No, it's not necessarily a kite. So what else can we do here? Okay. BD is a diameter that also tells us, okay, so BD is the diameter, remember? BD is the diameter. If BD is the diameter, then that has to make 90 degrees with the tangent, right? Because the diameter will be passing through the center of the circle as well. So the center might be somewhere here. We don't know where exactly that is, but wherever it is, this whole angle is going to be 90 degrees, right? Angle between the radius and tangent, angle between diameter and tangent, that is 90 degrees. So that tells us that this remaining angle here, what's that going to be? 90 minus 56, that is 34 degrees. Okay, why? Because this is 90. And now that's 34, and this whole angle is 90. What about this remaining angle in this triangle? We can find that now, right? That's the angle BDC. So we know two angles in that triangle already. One is 34 and the other is 90. Let's see what this turns out to be. 180 minus 90 minus 34. And that turns out to be 56 degrees. Okay, now that's one way of looking at this. That's one way of looking at this. And now that I've found it, I can think of a relatively more efficient way of doing this as well. So this is correct. This is 56 degrees. We could also think of it another way. And that is using the alternate segment theorem. Remember that? We did that in the last class. Alternate segment theorem. How could we use that here? Think of this triangle. So when do you use alternate segment theorem? When we have a cyclic quadrilateral, and there is a tangent that is touching one of those vertices. So we have the cyclic triangle. Sorry. So this yellow, we have this cyclic triangle, and there's a tangent at the point C like this. That's a tangent that we have, and the angle that you have here, this is 56 degrees, angle between the side BC of the triangle and the tangent. That is 56 degrees. If this angle is 56 degrees, then that means the opposite interior angle in that triangle, so the angle that is opposite to the side, that is also going to be 56 degrees. Right? That's what the alternate segment theorem says. That's also part of your syllabus. It's been recently added just this year. You need to make sure that you understand this as well. So you could use alternate segment theorem to write down this angle directly as 56 as well. Okay, all right, that is part C. Now angle ABC. ABC. All right, so that is this whole angle here. Now, what do we do about this? We can say we have this cyclic quadrilateral. ABCD is a cyclic quadrilateral. We know this complete angle. What's that? 52 plus 56. That will be 108 degrees. The opposite angle, it should be 180 minus that, right? Opposite angles, they have to add up to 180. So we can find this angle now, which is ABC. We can say it's 180 minus 52 and 56. So you can say minus 52 plus 56 using cyclic quadrilateral property. What do we get from this? 180 minus 108, and that should be 72 degrees. That's the angle ABC. Okay, now let's look at one last example that involves multiple circles. So these are the relatively more complicated types of problems when you have two circles like this. Okay, let's do one example in this, and then we move on to our next topic, which is HCF and LCM. And then we'll see if we have time to do functions today as well. That's a small thing. Let's see. All right, so points A, B, C, and D, they lie on circle 1. O is the center of circle 1. Points A, O, E, C, and F lie on circle 2. AEB and ADF are straight lines. Angle AOC is 146 degrees. Giving your reasons, write down CEA, CBA, and so on. Okay, now how do we think about this? Let's do it step by step. So what information are we given? We have some straight lines, we've got two circles, and we're given one angle here. This angle is 146 degrees. So that's the only angle that we know in this whole diagram. Okay, so we need to first write down the angle CEA, but the question says giving your reasons. That means you also have to mention which property you're using. That's why remembering those properties is really important. You can write down the property in your own words as well, and that's perfectly okay as long as the examiner clearly understands which property you are referring to. Okay, but you have to mention the reason for that. A reason for each of these answers. CEA. Okay, CEA. That's this angle here. What is this angle going to be? How do we think about this? You see, we know 146 degrees. This is the angle that we know already. Where is this angle coming from? This is the angle made by the chord. This is the angle made by the chord CA. So we can draw that chord to make it easier to understand. We have this chord, and this chord is making an angle of 146 degrees at the circumference here. Okay, this angle is 146. Now that same chord is making another angle here at the circumference. That's CEA. That's going to be the same. That's also going to be 146 degrees. All right, so we can use the property angles in the same segment, they're equal to each other. And this angle here, this is also going to be 146 degrees. So what do we do then? You write down that the angle is supposed to be 146 degrees, and then we have to write down the property that we're using, angles in the same segment. That's the name of the property. In your own words, you could write it's the angle coming from the endpoints of the same chord on the circumference, right? Angle at the circumference made by the same chord in the same segment. Or this is the formal name for the property, angles in the same segment. If you just write this down, that also will be sufficient. Angles in the same segment. Okay, they're equal to each other. CBA angle. What's this going to be? CBA, that is this angle here. Okay, so earlier, I was looking at the circle on the right side. Okay, so I was basically looking at this circle. So this angle 146 was at the circumference of that circle. And this was also at the circumference. So they were equal to each other. But now we're going in the other circle because they're asking us for the angle at this point B. B is in the circle on the left side. So now let's focus on the circle on the left side. And that is this circle here. Okay. Now, what do we know about this circle? The point O is the center of the circle. Now, the same chord CA is making an angle at the center, which is 146. And that same chord is making an angle at the circumference of the circle. So you see, it's coming from that same chord. It's that same chord that's making this angle at the circumference. Angle at center is twice the angle at circumference. So we can write down that angle. Then we can say CBA is going to be 146 degrees divided by 2, and that's 73 degrees. How do we know that? Because angle at center is 2 times the angle at circumference. You can write something like this or something else in your own words that makes it clear that this is the property that you're using. Angle at center is 2 times the angle at circumference. That's the property that we're using to write down that angle. This is 73 degrees. Okay, so that's another angle that we know now. Let me just write that down here, 73 degrees. Okay, next, CFA angle. CFA. Okay, CFA, that is this angle here. Okay, what about this now? Angle CFA. So now this is an angle in the circle on the right side. So again, we're going back to that circle on the right side. In this circle, the circle on the right, we have to find this angle. Okay. Now, what do we know about this circle? Yeah, so one property that you can use here is you can say, let's look at this quadrilateral. This is one possible quadrilateral that you could look at. You could also use E instead of O. But if you use this is a cyclic quadrilateral. And the circle on the right side, this is a cyclic quadrilateral with all its vertices on the circumference. And since it's a cyclic quadrilateral, the opposite angles, they have to add up to 180. This is 146. This angle that we have to find out is on the opposite side of the angle 146 degrees. So what do? We say that angle is going to be 180 minus 146 degrees, which gives us 34 degrees. Which property are we using? We're using the property of cyclic quadrilateral. Okay. Writing cyclic quadrilateral here, that should be enough because that tells us, that tells the examiner the property that you're using here. Okay, now this is 34 degrees. Let's write that down here as well. This is 34 degrees. Now, what's next? DCF. Okay, DCF. What angle is that? Okay, now that's interesting. DCF, we don't even have a line that's going from D to C. So we would have to draw that line ourselves. They're asking for this angle here. If I were to join the points C and D like this, the angle that we're looking for is this one here. That's what we're looking for. Now let me get rid of this shading again. Okay. How do we find this angle now? That's the next thing that we need to think about. Okay, so we have the smaller triangle. So this angle lies in this triangle, right? This is the triangle in which this angle lies. Now, we know one angle in this triangle already. Do we have this angle somehow? No. Can we find the outer one? Yeah. So if you look at the circle on the left side, this is a cyclic quadrilateral in that circle, the one on the left side. This is a cyclic quadrilateral, right? That means if this angle is 73, what about the angle opposite to it? It's going to be 180 minus 73. 180 minus 73, that is 107, right? And if this is 107, this is a straight line. Angle in a straight line, what's that? Angle in a straight line is 180 degrees. So this remaining angle here, this is going to be 73 degrees. And if that is 73, now we have two angles in that triangle. We can find the remaining angle, 180 minus 34 minus 73, and that should give us that last angle that we're looking for. So we can do something like this. We can say 180 minus 34 minus 73. What do we get from this? 73 and 34, that's 107, and that gives us 73 as the result. Now, which property are we using? We're using the cyclic quadrilateral property again to find the angle 107 first of all. And then we're using angle on straight line. That's kind of obvious. We don't generally need to write that. And then we're using sum of angles in a triangle. The circle property that we're using, that is cyclic quadrilateral. That's the most important one that you need to write down here. So first of all, we're using the property cyclic quadrilateral. And then along with that, we used sum of angles in a triangle. You can also write that if you want. This will suffice as well, but it's better that you write down the other property that you're using as well. That is sum of angles in a triangle. That is equal to 180 degrees. These are the two properties that we used here to find that remaining angle. Okay, I hope that was helpful. Now, in the exam, mostly if you have like 4 parts of this, 2 or 3 parts are generally going to be fairly straightforward. You can do them quickly. And then if you get stuck at any one of the parts after that, do not spend too much time on this, especially if it's something as complicated as this. Move on, do the rest of the exam, and then come back to it at the end. Leave time for it at the end. Otherwise, sometimes you can end up spending too much time on this, thinking about that 1-mark question. That's not worth it generally. So you would skip that for that point, complete the rest of the paper, and then come back to it at the very end. Okay, because generally it's not worth a lot of marks. Out of these 4 marks, generally 2-3 are going to be fairly straightforward. Like in this case as well, the first 3 marks were not that difficult. But in the last one, that I think made us think a bit more. So in case you're not able to figure that out in an exam condition, you would skip that for that point, and then you'll come back to that at the very end of the exam. Okay, all right. I hope that was helpful. Now let's move on to the next thing that we want to do today, since we have only around 25-30 minutes left. What I'll do is I'll do the bigger topic first amongst the 2 that I was thinking of doing today. One was HCF LCM and the other functions. Functions is fairly straightforward. Its questions are also not that difficult. But HCF and LCM, although the topic is fairly straightforward, its questions sometimes are quite tricky. So I'll start with this and see if we can complete this quickly. And then if we have time, we might be able to talk about functions at the end as well. Okay, HCF and LCM of a set of numbers. Okay, now the idea is fairly straightforward. That is something that you are already familiar with since very early years, maybe grade 6, grade 7. But then some questions on this are fairly tricky, so we will focus on practicing more. But let me quickly remind you about the idea of HCF and LCM, what they mean. Let's do that using a set of numbers. Let's say we have one number that is 84, and we have another number that is 126. Okay. Let me write that down here. Okay. Now, let's say you're asked to do something like this. You're asked to write down 84 and 126 as the product or as products or their of their prime factors, and hence find their LCM and HCF. Okay, now what does HCF stand for? HCF is the highest common factor. Now we'll understand those exact definitions through this example as well. But let me just write down the full forms first of all. What's HCF? HCF is the highest common factor. And LCM is the least common multiple. Okay, now how do we actually find those two things? Let's understand that using an example. So we have to write down 84 and 26 as the product of their prime factors, and then we have to use that prime factorization to find their HCF and LCM. Now, how does this process work? This is one way of doing this, that you do them together like this, or let's do them separately first. So 84 and 126. Let's find their prime factors. Now, this is how most of you are used to doing it. That you make a structure like this, and then you start dividing these numbers by the smallest factors that you can find for them. 84, the smallest prime factor that you can find for it is 2. So you write 2 here, divide 84 by 2, and that gives you 42. Okay, we can again divide it by 2, and that gives you 21. We cannot divide by 2 anymore. What's the next prime factor, that prime number that you have? 3. Can you divide by 3? Yes, 3 works. And that gives you 7. 21 over 3, that's 7. And now, which prime number do we use next? That is 7. And that gives you 1 at the end. And now you can say that 84 can be written as 2 times 2 times 3 times 7. Okay? Or you can say that is 2 squared times 3 times 7. That is 84. All right. What about 126 now? Let's do the same thing with 126 and see how that can be written. Again, we can divide by 2 first of all. When we divide it by 2, we are left with 63. We cannot divide by 2 anymore. What about 3? 3 works. 63 over 3 is going to give you 21. You can divide this by 3 again. 21 over 3, that's 7. And you can divide by 7 now. And that leaves you with 1. So you can say 126 can be written as 2 times 3 times 3. That is 3 squared times 7. This is the prime factorization of both of these numbers. Okay. Now, how do we find the HCF and LCM from this prime factorization? How can you find the HCF and LCM? Now for HCF, remember HCF, that's a factor. Factor is a smaller number, right? So for example, if you have 84, let me write that down here. 84 has a number of factors like this. 84 has 2 as a factor. It has, in fact, let's start from 1. 1 is also a factor, although it's not a prime. But let's write down all possible factors for 84. We have 1, we have 2, we have 3, 4 as well, and then 5, 6 as well, 7, 8, 9, 10, 11, 12. 12 works. Yeah, 12 times 6 is 84. And then 4 times 21. And then 3 times 20. No, 3 times 24. 26. 28. Yeah, 28 works. 28 into this. Yeah, so I just want to show you what highest common factor means first, and then we'll find that in a moment. Let's write down all the factors first of all. 1, 2, 3, 4, 6, 12, 21, and 28. 28 is a factor, right? 28, 56, and yeah, that works. And then you have 2 times that, that's 42, and then finally 84. These are all the factors of 84. And then similarly, if you were to write down all the possible factors of 126, what are they going to be? 1, 2, 3, 4 is not a factor, 5, 6, 6 is a factor, and then 7, 8, 8 does not work. 9 is 9 a factor. 9 does seem to be a factor. 90 and then 36, yeah, so 9 is a factor. And then 10, 11, 12, 12 times that is not 13, 14, 14. 9 times 14, yeah, so 14 is also a factor. And then 126 over 6, that is 21. And then 126 over 3, that will be 42. And then 126 over 2, that is 63, and then 126. Okay, now you won't have to do all of this when you're finding the LCM and HCF yourself, but this is just to explain to you what we mean by the highest common factor. So these are all the factors of 84, and these are all the factors of 126. The highest common factor is the factor that is common between them. But now there are many of them. 1 is common, 2 is common, 3 is common, and then you have 6 common as well. We're looking for the highest common factor, the largest number that's a factor of both numbers. Okay, that's what HCF means. The largest number that's a factor of both of these numbers. Now, what's the largest of these all? That is 42. 42 is the highest common factor of these two numbers. Okay. Now, how do we find 42? Now, in this case, I wrote down all the possible factors. That's going to be quite tedious. You won't always be able to do it quickly. How do you find out this number 42 quickly? What's the way to do that? We use this prime factorization for that. How are we going to use it? Let's write down the two prime factorizations here like this. 84 is 2 squared times 3 times 7, and 126 is 2 times 3 squared times 7. For each prime factor, for HCF, what you do is you take the lowest power of each prime factor. The lowest power, or I can say take the smallest power of each prime factor. Okay, now what do we mean by that? We've got 2 squared here and we have 2 here. So one prime factor is 2. That's common between both of them. What's the smallest power? This has power 2. What about this? This has power 1. You just take the smaller powers. Okay. So HCF is going to be 2 power 1, right? That's the smaller power amongst the 2's. Then what about 3? What's the smaller power for 3? This is 3 power 1. This is 3 power 2. The smaller power is 3 power 1. So you say you take 3 power 1 and then 7. What's the smaller power for 7? Both of them have 7 power 1. So the smaller is also 7 power 1. you take 7 power 1, and that is going to give you the LCM. That's, sorry, HCF. That's 2 times 3 times 7. That's 42. That's the highest common factor of these two numbers. Once you have those prime factorizations, you can just take the highest powers from these prime factorizations. Okay. Now, what is LCM? Least common multiple. Now, 84 has a lot of multiples, right? For example, we can multiply 84 by 2. So multiples of 84, what would they be? 84 and then 168 and then 252 and so on. And similarly, 126 has a lot of multiples. Starting from 126, we have 252 and so on. What's the least common multiple? The smallest multiple that is common for both of them. Now, let me write them on the side here. These were factors. If you were to write down their multiples, for 84, we would have 84, 168, 252, and so on. For 126, we would have 126, then 252, and so on. This number 252, that's the first common multiple that we're getting. First number that is a multiple of both of these numbers. That is the LCM. Okay. So you see, factor is a smaller number. LCM is a bigger number. How do you find LCM from that prime factorization? The way to do that is, once you have this prime factorization, for LCM, you take the largest power of each prime factor. The largest power of each prime factor. Okay, now what does that mean? What is the LCM going to be here? Let me just represent that in different color. What about LCM? How do you find that here? Take the highest powers. Okay, so we have 2 power 2 and 2 power 1. What's the highest power amongst those two? 2 power 2. So you say the LCM is going to be 2 raised to power 2 times the highest power of 3. One of them has 1 power, the other has power 2. What's the highest? That's power 2. That's what we use here, 3 power 2. And then for 7, both of them have power 1. What's the highest? That's 1. So we just use 7 power 1. And that is going to give us the LCM. What's that? 2 squared is 4. 4 times 9 is 36. 36 times 7 should give you 252. That's the LCM of these numbers. Now, this is important to remember. For HCF, you take the smallest power of each prime factor. For LCM, you take the largest power of each prime factor. Okay, and that should give you the result. Okay, I hope that makes sense. That's the idea. That's how you find HCF and LCM. You can do this for 2 numbers. You can do it for 3 numbers. Let me quickly do it for, let's say, 3 numbers. If we had something like this, maybe smaller numbers, that might be quicker to calculate. If we had 3 numbers, let's say we have 24 and we have 36 and 60. We have these 3 numbers. What is their prime factorization going to be? You can find those prime factors using this method again. Okay, now let's suppose you've done that. Let me write down the prime factors. Directly, they would look something like this: 2, and then you have 12, so 2 again, and then 2 again, and then 3, right? So 24 can be written as 2 cubed times 3. That's 24. Okay. Now, what about 36? 2 into 2 into 3 into 3, and that's going to give us 2 squared times 3 squared. That's the prime factorization for 36. 4 times 9. Yeah, so that works. For 60, we can say 2 times 2 times 3 times 5. And that can be written as 2 squared times 3 times 5. So we have these three numbers. We have their prime factorization. That looks like this. Okay. Now, how do you write down the LCM and HCF? For HCF, you take smaller powers because factor is supposed to be a smaller number. And for LCM, you take the bigger powers. Okay, now let's start with HCF first of all. Which prime factors do we have here? We have 2, we've got 3, and we've got 5. These are the three numbers that we have. Let's write them down here. 2, 3, 5. And similarly for LCM, 2, 3, and 5. These are the three numbers that we have in all of these prime factorizations, right? Three different numbers are 2, 3, and 5. What powers do we use here now? For HCF, we use the smaller powers. Okay, so what's the smallest power of 2? 3, 2, 2. The smallest power is 2. So we use 2 here. For 3, the smallest power is 1, right? This is 3 power 1, this is 3 power 1, this is 3 power 2. So this is going to be 3 power 1. And then for 5, what about 5? What's the smallest power of 5? Any idea? This is 5 power 1. The other two do not have any 5. If they don't have any 5, we can think of that as that they have 5 power 0, 5 power 0. They don't have anything, right? So they have power 0 basically. So 0 is the smaller power. In HCF, we don't have any 5. So that's 5 power 0. You can just ignore this as well. And that gives you 2 squared times 3. That's 4 times 3. That's 12. The HCF is 12. Okay, so the smaller power is for 5 is not 1. 5 is not even there in the other two factors. That means in the other two, we have 5 power 0. That's just 1, right? Anything raised to power 0 is 1. So this is just 5 power 0. So the smaller power for 5 is 0. Okay, what about HCF? What about LCM now? For LCM, we take the higher powers, the bigger powers. Okay, what's the biggest power of 2? That's 3. That's what we use here, 2 power 3. For 3, the biggest power is 2. So we use 2 here. For 5, this biggest power is 1. That's what we use here. 2 cube is 8. 8 times 9, that is 72. 72 times 5. 72 times 10 is 720. Half that will be 360. This is the LCM, that's 360 of these three numbers. Okay, let's have a look at some examples now. It turns out we won't be able to do functions today, but let's do some examples in this. We'll leave functions for later then. That's a small thing. Let's have a look at some questions on prime factorization quickly. Okay, so let's do this one first, in which we have to evaluate a square root as well. So sometimes they want you to evaluate square roots, cube roots using prime factorization as well. So how do we start with this? They first of all want us to express 7056 as the product of its prime factors. Okay, now how do we do this? This is from non-calculator paper. That means you cannot use calculator, and mostly this question comes in the non-calculator paper. Okay, so how do we do this now? Let's do it step by step. Okay, 7056. Just give me a second. Quickly. Okay, 7056. What do we divide it by first? We can divide it by 2, and that gives us 3,500. So 7,000 divided by 2 is 3,500, right? So we have 3,500, and then 56 divided by 2, that's 2,83528. We can divide it by 2 again. Okay, what would that be? 35 divided by 2, that is going to be 17 point something. So we can start with 17. Okay, then we have 128 left. 128 over 2, 12 over 2 is 6, and then 8 over 2 is 4. 1764, that's what we get and divide by 2 here. Okay, let's divide by 2 again. 1764 divided by 2. 17 divided by 2, that will be 8 point something. So we start with 8 here. That leaves us with 164. 164 over 2, that will be 82. 882. Okay, we can still divide by 2. 88 over 2 is 44, and then 2 over 1 is 441. Now we cannot divide by 2 anymore. Okay, so now 441, can we divide that by 3? Remember, how do we check if a number is divisible by 3 or 9? A number, we can check if a number is divisible by 3 or 9 by just checking if the sum of the digits is divisible by that number. So for instance, in this case, the sum of these digits, 4 plus 4 plus 1, that is 9. If 9 is divisible by 3, that means this number is divisible by 3. So we can divide by 3. This rule works for both 3 and 9. Okay, you would have done this in your grade 9 at some point, or grade 8 maybe in D1. So if the sum of digits of a number is divisible by 3, that means that number is divisible by 3. If the sum of digits of a number is divisible by 9, that number is divisible by 9. So this property works for both 3 and 9. So this number can be divided by 3. So the next number that we can have here is 3, not 2. Okay, 141 left. Okay, 14 over 3, that will be 12 over 3, that's 4, and that leaves us with 21. 21 over 3 is 7. So 441 over 441 over 3 is 147. Okay, again, can be divided by 3 again. That should work. 14 over 3, we can have 4 here, and then 27 over 3, that's 9. And then we have 49 over 3, and we can't do it by 3 anymore. 5 doesn't work, 7 works, 7, then we have 7 and 7 again. This is the prime factorization that we get for this. Okay. Now, how do we write that? We have 4 2's, so we can write that as 2 raised to power 4 times 3 squared times 7 squared. That's the prime factorization, 2 raised to power 4 times 3 raised to power 2 times 7 raised to power 2. Okay, now that we have done that, they want us to evaluate this. Now, what does that mean? We can write 7056 as this, right? We have done that in the first part. Now, if we had to find the square root of this, we can say it means 2 raised to power 4 times 3 squared times 7 squared. Square root means power 1 over 2, right? Now, these are multiplying, so we can use indices rules here, right? This power can come inside and get multiplied with each of these powers. So this becomes the second part, 2 raised to power 2 times 3 raised to power 1 times 7 raised to power 1. You can evaluate this and see what this is. 4 times 21, and that will be 84. This is 84. That's the square root of 7056. Once you've done the prime factorization, you can use that to find square roots and sometimes cube roots as well. Okay, this is what we get. Let's move on. Let's do a slightly more complicated one. Yeah, let's try this. Written as the product of its prime factors, 360 is equal to this. Write 108 as the product of its prime factors. First of all, again, you can follow that same process. 108 divided by 2, that gives us 54. Divide that by 2 again, and that gives you 27. Now you can divide by 3. That gives you 9, and then 3 again, and then 3 again. So this prime factorization for 108, it would be 2 squared times 3 cubed. Right? You can write that here that this is 2 squared times 3 cubed. 27 times 4, that's 108. Now we need to find the least common multiple of 108 and 360. Give your answer as the product of its prime factors. Okay, now what do we do for this? LCM, multiple. Multiple is a bigger number. So we take the highest powers of each factor. What are the different factors that we have? 2, 3, and 5. Okay, 2, 3, and 5. What's the highest power of 2? We've got 3 here, we've got 2 here. The highest power is 3. So we say it's 2 raised to power 3. 3 squared, 3 cubed. What's the higher power of 3? That is 3. And then 5 power 1. And this is basically 5 power 0. The higher power of 5 is 1. So we use 5 here. They want us to give an answer as the product of its prime factors. So we can leave it like this. The LCM is going to be 2 raised to power 3 times 3 raised to power 3 times 5. That's the LCM. Okay. Now they want us to find the smallest positive integer k such that 360 times k is a cube number. Okay, 360 times k should be a cube number. Now, what does that mean? 360 times k. What's 360? We know this is 360. So we can write this as 2 power 3 times 3 power 2 times 5. We have to multiply it by some number k such that this thing becomes a cube number. That means each prime factor should end up getting a power of 3. Now this is 2 cube already, that's already a cube. This is 3 squared. If we want to make it 3 cube, what do we have to do for that? We have to increase this power by 1. So that means k is going to have 3 power 1. Okay, so that 3 power 1 into 3 power 2, this becomes 3 cube. Okay. And then we have 5. That's 5 power 1. If you want to make it 5 cube, we can multiply it by 5 squared. So that 5 squared times 5, that would give us 5 cube. And then that whole thing will become a cube number. If we take cube root of that, then the powers 3 and 1 over 3, they will get cancelled out and you would get an integer from that. That means that will be a cube number. So k therefore is supposed to be 3 times 5 squared. That's 25 times 3, which is 75. So if we multiply 360 by 75, that would be a cube number. So k equals 75 here. All right. I hope that makes sense. Let's do one last example. Then you can complete this worksheet. And if there are any questions, we can discuss them in the next class then. Okay, let's do this one. The second part. The numbers 225 and 540 written as the products of their prime factors are 225 equals 3 squared times 5 squared and 540 equals this. We have the prime factorization given. First of all, they say write 2250 as the product of its prime factors. Now, how is 2250 connected to any of these numbers? 2250 is basically just 10 multiplied by this number. So 225 times 10, that is 2250. That means we can get 2250 if we have 3 squared into 5 squared times 10. Okay, but 10 is not a prime number, so we have to break that down. How do you break 10 down? That's 2 and 5, right? So it becomes 3 squared into 5 squared into 2 into 5. Now write that properly. And that will give you 2 into 3 squared and then 5 squared into 5. That becomes 5 cube. So this should be 2 times 3 squared times 5 cube. That is 2250. Now, this is interesting, this next part now. It says, find the smallest positive integer value of n for which 225n is a multiple of 540. Okay, so 2 to 5n should be a multiple of 540. In other words, they're basically asking you for the LCM. Smallest number n such that when it's multiplied by 225, it gives you some multiple of 540. So the number that we're talking about, it will be a multiple of both 225 and 540. So we can, one way to do it is that we find the LCM, and once we have the LCM, we just divide that by 225. Or a relatively easier way of thinking about this would be, what's 225n? 225n is 225 is 3 squared into 5 squared. That's 225, right? Let's write that here. 3 squared times n. This should be some multiple of 540. Okay, that means if we divide this number by 540, we should get an integer, right? For example, if we have 20, that's a multiple of 5. 20 over 5, what does that give you? That gives you 4. This means that 20 is a multiple of 5. That's why when we divide 20 by 5, we get an integer answer. So if we do 225n divided by 540, that should be an integer. Okay. Now, how do we make this an integer? What's 540? 540 as its prime factors is 2 squared into 3 cubed into 5. Okay. Now, what do we place in place of n here? What do we write in place of n here so that the result from this division ends up being an integer? Let's think about each prime factor one by one. We have 2 squared in the denominator. Do we have any 2 squared in the numerator? No. We don't have any power of 2 in the numerator. In order to cancel this thing out with some number in the numerator, we need at least 2 squared in the numerator. So n, for n, what we can do is we can say in place of n, what can we input here? Number one, we would need a 2 squared here, so that this 2 squared and this 2 squared, they get cancelled out with each other. And the result turns out to be an integer. What about 3 squared? We have 3 squared there and we have 3 cubed here. If we want to cancel out the whole of this 3 cubed so that the result turns out to be an integer, we need a 3 cube in the numerator. Right now we have 3 squared in the numerator. We want 3 cube. What do we multiply it by? In the numerator, to get 3 cube, we multiply by 3, and that would give us 3 cube in the numerator so that it gets cancelled with 3 cube in the denominator. So we have 2 squared times 3 in the numerator. And then what about 5? Now 5 is not a problem because we have 5 squared in the numerator. 5 squared over 5, that's already an integer. So we don't have to do anything for 5. That means n is 2 squared times 3, that is 12. So if we multiply 225 by 12, the number that we get, that's going to be a multiple of 540. Or you could find the LCM of these two numbers. Whatever that LCM is, you could divide that by 225, and that will also give the value of n. That's a bit harder to think of. You need to have your LCM concept very well understood for that. I would say for most people, this will be easier to think of. Okay, now I'll leave you with this. Attempt more questions from this worksheet. If there are any problems, you can let me know about them tomorrow. This is one good one, by the way. I would encourage you to attempt this at least. and then more apart from this as well. And then we will discuss any problems that you have in the next class, then along with moving on to the next topic, which is most likely going to be mensuration, inshallah. All right, that's it for today. I'll see you again in the next class then. Allah Hafiz. Thank you.